Thank you. Okay, so thank you for coming. Thank you, Céline, Thomas, and Fabian for inviting me as well. As Thomas said, I'm going to talk about my PhD project I'm doing now. I'm working in Toulouse, France, in LAS and IRIT. I'm going to talk like an overview about our project, about our work. As it says in the title, it's about control of Markov-Modulated Restless Bandits. And I'm going to talk about different approaches. We have different ideas. We already finished one. We are finishing the second one now. And we have some ideas to continue afterwards. So I'm going to explain them. You can interrupt if you have questions or anything. I'm trying to also to give some introduction about the theoretical tools we use. I don't know how much you know about them. And then I'm going to talk about a particular problem. So what's the motivation? What we have? So for the introduction, I'm going to speak what's the motivation for our problem. We are working with bandits, which are a particular case of Markov decision processes, which are a tool that is widely used in different frameworks. But in particular, we are interested in scheduling over queues, over different queues. So the motivation, the original motivation is something like this. We have a typical scheduling problem. So we have different queues, like we see here, and we have to choose which queue we are going to serve. So we cannot serve all queues at a time. So we have different rates. We have lambda, different lambdas for arrivals, different mu's for service times. And what we are adding here, what we call modulated bandits, modulated queues, are changing conditions. So what we have is an environment. It's this environment we have here, d of t, which is changing, is an independent Markov process, it's a random process who's changing its state. And when it changes its state, it changes the rates for the queue. Okay, so we have a classic queuing problem with changing conditions. This is a Markov decision process, so we are going to have some cost to pay in each state the queues visit, and the decision to make is which one we are going to serve. Okay, so a classic problem for queuing is the cost is a linear cost, for example. So if we have more customers in waiting for service, we have more cost to pay, and etc. There are many motivations for this. For example, yes.
Do you know the arrival rates and on the service rates?
So if we know the parameters, yes. Yes, we are going to assume as an hypothesis that we have all the parameters now. In fact, yes, I'm going to talk about the different settings. So we may change the hypothesis if we know the transitions of the environment, but the transitions of the queue, we are going to know them. Okay? Different examples we may take, for example, are these one are when we have cloud computing, when the arrivals vary according to time. It may depend on how many, on some environment, it changes how many customers arrive. Also the quality of some wireless downlink, etc. So this is the idea, the main idea, but there are many tools I have to define before going directly to our problem. So that's my what I want to say. Like an overview, we have Markov decision processes, as I was saying, in particular bandits, the ones we use. There are something that are called Whittle's index methods. Something Whittle developed 30 years ago for bandits. And modulated stochastic processes, which is something that is more used for queues without decisions, or even for particle systems, but not much for bandits. And as I was saying before, we have different projects. There's one we already published in Sigmatics this year. There's one we are finishing now, and one we want to do afterwards. In the first one, the main hypothesis we are going to have a fast environment. So that means that the environment is we are going to take the limit. We are going to work in an asymptotical meaning. So it means that we are going to take a mean field limit about the amount of queues or the amount of bandits. And in the same limit, we are going to scale the speed of the environment. So the environment is going to work much faster than the normal speed. And in that case, we cannot observe the state of the environment. We're going to propose policies, so actions that do not see the actual state. The only thing they know is the invariant distribution of the environment. That's the first work. In the second work, we are going to assume that it doesn't scale. So we have a normal environment in a normal speed. We can say it's not going to infinite. And in that case, we can observe the environment. We can observe the state. And the policies are going to depend on the state of the environment. And at the end, we would like to work with a normal speed as well, but we don't know the parameters of the environment, so we would like something about learning and bandits learning how the environment gets transitions. Those are the ideas. Any question up to here? Now I want to define some things. So I start by the beginning. I don't know if you know already about something about Markov decision processes. It's just one slide, but to give a general overview. What we have here is we have a normal Markov process, so exponential times from one state to another. But we have to add actions and coasts. So for example, we have this is a simple random walk, we could say, with actions. So the states are S0, S1, and S2. And in each state, we have to choose an action. For example, in S0, we can choose A0 or A1, where A1, it means here that we have a deterministic transition with probability 1 up to S2. But this one here, if we take A0, we have 1/2 coming back to S0 and 1/2 going to S2. This is for a discrete time, okay? So probability going from one state to the other one. Those are the actions we can take, and it's the same for each state. And then we have costs or rewards. We can see it has the same idea. Here we have a negative reward, so we don't want to go there. But here we have a positive reward, so we would like to do this transition. So in this case, a basic Markov decision process, where what we would like to do is to end by passing over here. That's the idea, and we normal in this, as it says here, optimization problems arises. These kind of problems where we want to optimize to maximize some value function in some and different kind of time being. These are the classic Markov decision processes. The ones we are going to use are the bandits. What are bandits? Bandits are these kind of machines, so the machines for money. The idea is we have n different processes working at the same time, and we cannot pull all the machines at the same time. So it's the same idea as I was saying for queues. We cannot serve all the queues at the same time, and we want to choose which one to serve. Here for these machines, we would like to say that at the end of the problem, which can be in finite horizon or infinite horizons or in infinite time, we would like to maximize the reward we get from these machines, okay? Each machine gets different transitions and different costs, and we have to choose which one to serve, which one to pull in this case. So we are going to have two different actions, which make it easier to work with. We're going to have one action, which is passive, and another action, which is active. The one which is active is the one we pull, or if they are queues, is the one we serve, okay? And we have to make a decision in each moment on time. So for each t, we have n different bandits, which we are going to call an index k. We are going to have exponential rates, as they are a Markov decision process. For a Markov decision process, when we have a policy, so it means for one state is fixed, the action we're going to take, we come back to a Markov process, a normal Markov process. So it means here that we fix the action, for example, action A, 0, 1, we are going to have exponential rates from state I to state j. So this is a classic Markov process once we have fixed the action. So those are the transitions for the bandits, and there's a particular model where we work, which is called the Restless Model. What is the Restless Model? Is this one, where we have the action is 0, so passive. We may still have some transitions. The queue may also change its state even if we are not serving. For example, if we have arrivals. Okay, we will not serve the queue, but it can change its states +1 because there's one arrival. Those are Restless models, and we cannot make all active at a time. So we are going to call a fixed proportion of bandits which we can make active are going to be alpha. Okay, this is the setting for bandits, the classical setting. We are going to call pi different policies. So the policy that says which action we take in each state j. Policy will not depend on time, so we are going to consider homogeneous policies. And we have an optimization problem. Which is the optimization problem? Okay, we have to define, we have B for the state of the bandit under policy pi. We're going to have the cost function C. And for policy pi, we're going to define this expected cost, which is V, which depends on n and pi. It depends on pi because it's the policy. It depends on n because we have fixed amount of bandits, which is n. I have to put this because then I'm going to take n to infinite. Okay, I'm going to take some limit on the amount of queues. So it's important to use this notation. And we have, this is the value function, the expected cost we want to minimize. We have to find over all possible policies which policy minimizes this, with the constraint about the fixed amount of bandits that can be made active at a time. Yes.
What is the motivation for this constraint?
Yes. The motivation with the constraint means that we cannot make active all bandits at a time. So for example, if we understand that they are queues, it means that we cannot serve all queues at a time. If we have n queues, we say, okay, we do not have resources to serve all queues at a time, and that's the idea of the optimization problem. Which queue can we serve?
But this is a soft constraint? So you say that the sum from 1 to n over all a's, which is passive or active decision?
Yes, so this is 0 or 1.
0 and 1, so this can be a percentage of the bandit.
Yes, for example, if alpha is a half, it means that the half of the amount of bandits can be active at a time, exactly alpha. Okay.
How does this connect to the service of 1 queue?
If, for example, we have 1, alpha is equal 1 over n, so it means that only one can be 1 and all the others can be 0. To any alpha, yes.
Okay,
yes, a general model, yes.
Okay.
So in fact, for the first bandit problem, alpha is equal 1 over n. So alpha is just one bandit that can be active at a time. Then we generalize it to many bandits. So we have to choose alpha is strictly lower than 1, but it may be many more than 1 over n. And yes, so this is like more general framework for bandits. So we can make active more than 1. And we're also going to consider restless bandits, what means that they can change their state even if they are passive. So this is like a more general framework, but the original idea is that you cannot serve all the bandits at a time. Okay? But in fact, that's an interesting question because here it's a fixed constraint for all time t, and that's something we are going to change, or it's something that is already been changed for when they were looking for some solutions, because we have to relax this constraint. What I was saying in connection to the question you were asking, the original problem where only one bandit can be active and they are not restless has already a solution. It's been studied by Gittins, and he found an optimal solution, an optimal policy that works, so they are called the Gittins index. But then the generalization, where alpha is not only one bandit, and when we have restless bandits, so they can change their state even if they are passive, there is no solution, and it's also proved that the problem is NP-hard. So we cannot find a solution in this general framework, and that's why Whittle proposed a relaxation. And this is the relaxation I'm going to talk about. We have the relaxed version, where we simplify the constraint. This is still the proportion of bandits over time, but here is a mean value over the time from 0 up to infinite. And it's not a fixed constraint for each moment on time. This relaxation allows us to find some heuristic, and Whittle used this heuristic, because what he did is he used the Lagrange multipliers approach, which means that we can change the constraint. The Lagrange multiplier assures us that we can find some W, some multiplier W, which makes that the problem we want to minimize is this one without the fixed constraint we had before. And this problem, in order to minimize this formula, is much easier because we can decompose it in n different problems, because we can take the sum out of the mean value, and we can say that we are only going to study one bandit at a time. Okay, that's the relaxed version. The relaxed version allows us to work only with one bandit, and we're going to study the behavior only for this parameter for this bandit. Yes?
So basically, the A's will continue to be discrete variables, binaries.
Yes, 0 or 1, always 0 or 1.
So how do you guarantee that there is that the Lagrange relaxation is tight? Because does it come from a proportion? So basically, because you take the limit as t goes to infinity,
yes,
the integral, then you kind of have a continuous relaxation for the proportion of time, for the proportion of because otherwise there is no guarantee basically that the Lagrange relaxation is
yes, I see what you mean. Here we have still that this depends on the function is all over R, so we have a continuous time variable, and I think it may work as well. So you mean that the Lagrange approach we have
correct for continuous
for a function? Okay. I should check this question. It's a good question.
Maybe because you take the limit to take those infinite integration, maybe you, I don't know, you make appear some kind of frequency of.
Okay, yes, I have to check. It's a good question.
It's relaxed as well, no? It's a continuous.
No, the variables is still 0 or 1 because they are not. There's no other meaning about having a bandit half active, we would say. Okay, it's a good question. I have to check it. Yes, still it's the classic Lagrangian approach. It's not a different theorem we are using. And yes, we are using the constraint for A, where still A can be 0 or 1. Yes, that's for sure we're not changing. I have to check the hypothesis now about the theorem. I don't have it now in my mind, but it's a good question. Thank you. Anyway, what we are going to solve now is this. If we assume we can use this approach, we're going to solve this subproblem. So we have n different subproblems. We are now working with just one bandit. And this is still a relaxation, so it's another problem. We cannot assure that the solution for this problem are going to be the solution for the original problem. But however, we have some things we can say. So that's what I'm going to talk about now. This is a bit more technical. And it's important to know that here I'm just giving the introduction about some work Whittle did before. So this is the classic bandit framework. Then I'm going to talk about our problem with the environment and with the modulated situation. But here I want to say this thing before going to our problem, because we are going to use this approach, Whittle's proposal. So what Whittle showed is that there are some conditions which are called indexability conditions. I'm not going to give all the details here because they are long conditions, but which are, however, some intuitive conditions we can give to the system. Under these conditions, we can find some threshold. What is this threshold? It's a threshold that depends on the state where the bandit is. And if the multiplier is below this threshold, the optimal policy that we have is active, is making it active. And if the multiplier is over this threshold, the optimal policy is going to be passive. This is what we call, in case we have the threshold, or these indexability conditions, that's what we are going to call the Whittle index for each state. So for each state, J. These are this is the solution Whittle proposed. And this solution is shown to be optimal for the relaxed problem. So this means that this gives a policy, which means that given the Lagrangian multiplier, we're going to make active the bandits that are in the state that are that have the multiplier over the multiplier, that have the index over the multiplier, sorry. And for the original problem, so where the constraint was not relaxed, it has been to be a good heuristic with a good performance in the original problem when n is fixed. And if you take n to infinite, we can show that it's asymptotically optimal as well. Okay, so it works for the relaxed problem and also for the original problem if we take n to infinite. This is where we're going to work in some asymptotical regime. That's what we propose in our problem. And that's why we take these ideas. So going to our model now, now what we propose is something that we have the bandits, the classic bandit framework, and we take ideas from some work done over modulated particle systems. So what we propose is we still have n bandits evolving in a finite state space, so we have the same framework as the original bandits, and what we are adding here is an independent Markov process, which we call d of t. We assume it has a stationary measure. We're going to call it phi of d. And when the environment visits the state d, what we have is that we have a cost that depends on d, and also rates that depend on d. Okay, so it's the same framework, adding an environment that changes the rate when the environment changes its state. Okay, it's important to note that in the first model we have this 1 over n as an extra factor. When n is fixed, it doesn't change anything. But when we take n to infinite, it means that the rates for the bandits are going to 0, which means that if we see it the other way around, it means that the environment is going to move much faster than the bandits. This is why we consider non-observable policies, because in a small moment of small lapses of time, what we're going to have is infinitely many changes on the environment. And that's what the policies, what we propose, do not observe the environment, but they only know the stationary measure of the environment. In the asymptotic regime, as I was saying, we take n to infinite, so both the number of bandits and the speed of the environment are going to be scaled. And in our case, we want to show an asymptotic optimality. So not only an optimality, but also an optimality in the meaning of n going to infinite. So that's why we have this definition. So pi star is going to be asymptotically optimal if we can show this property, that taking n to infinite, for any other policy, the expected value is going to be over the expected value for pi star. This is what we want to show. In order to do this, what we do is to work in the fluid model. What does it mean? I mean that when we have n fixed bandits, we can see the state of each bandit. If we take n to infinite, we're going to have infinitely many bandits. We cannot see the state of each one. So we change the perspective of the problem, and we see the proportion of bandits in each state. So we're going to have a proportion in state 1, a proportion in state 2, a proportion in state 3. Okay, so we start watching to the fluid model. We have this new variable x, which is going to define the average behavior of the system. And as we are taking n to infinite, now we have to consider an average rate. What do we mean with average rate? We take the exponential rates we have, q, that depend on d, with the average given by the stationary measure of the environment and the random variable associated to the environment. Those are going to be the average rates and also the average cost. And we consider now a fluid model whose dynamics are defined by the average parameters c over line c and over line q. That's what we consider. For this fluid model, we can define a linear optimization problem where we want to minimize the cost, the overline cost, so the average cost we got with this constraint. So we want the equilibrium of the linear optimization problem given with the average rates. And these linear optimization problems, the equilibrium points of these linear optimization problems, are going to give us the optimal policies for our problem. Okay? So taking in mind this linear optimization problem, what we do is we define, and we can show there is an optimal solution of this problem. So the solution set is not empty. And we have x star is going to be the solution of this problem in the equilibrium sense. We're going to define the expected value for this x star. And what we can show is that if we take the policies that make converge the fluid model to this x star, for the fluid model, they also work for the stochastic problem. So we come back to the bandit problem, and we can show that this set of policies for the bandits are asymptotically optimal. So this is the main result. We can show this optimality. I'm going to talk about the ideas we use for the proof. Maybe I'm not going to get into the details because there are many technical details, but I'm going to give some details here. So we want to show that these policies are the policies that may converge, give an asymptotic optimality for the bandit problem. So what we have to do is to relate the bandit problem and the fluid model when we take the limit in n. That's the main idea. So what we're going to show is that v star, so this the expected value for x star, is going to be a lower bound. And we prove an asymptotic independence between the bandits, because the bandits are not independent before taking the limit. Before taking the limit, the bandits can tell us something about the environment, and if we know something about the environment, it may tell us also something about other bandits. But what we can show is that in an asymptotical sense, we can take the limit for the environment, and in that case, we are going to get an asymptotic independence. And with this, we're going to use some results, a paper from Bordenave in the year 2010, where he shows the behavior of a particle system when we take the amount of particles to infinite. We can apply this directly for our problem, and we can show that this kind of policies converge to the equilibrium in the fluid model. And that shows us that this is going to be the optimal policy for our case. This concludes that the expected value for pi star is going to converge to this lower bound. So this means that this is the optimal solution for this asymptotic regime. Those are the proofs. Those are the steps of the proof, sorry. We can give an example, and then it's where I have to come back to Whittle's index, so the relaxation we have and the Lagrangian multipliers. Whittle, already, as I was saying before, Whittle proposed some set of policies that are optimal for the relaxed problem, for the original bandit problem when we don't have environment. Here we have an environment, but what we can do, and what we proposed, is to take another bandit problem without environment, where the dynamics are given by the average rates. So I mean, in our modulated process, we have rates that depends on D. We propose another problem where we have now rates that do not depend on D, but are the average of the rates that depended on D. So we have this new problem, and this comes back to the original bandit problem where there is no environment. So then we can define the Whittle index for that model, and that's what we call the average Whittle index. So the average Whittle index is the Whittle index for this process where we have the average rates. And what we can show is that these policies are included in our set of policies. So these are asymptotically optimal in our problem. And this is good because also we can simulate these problems in MATLAB. And we can get the performance. So that's what we did. We took these policies to our original problem. So I came back to the queuing problem. We have different queues whose rates depend on D. We have the decision to make, which is which queue we want to serve. And what we do is we compute these different policies. We get the performance of an optimal policy with a value iteration approach. And we also show that the average Whittle index is something we can define, and we can calculate its performance. And that's how we get these results. We have different performances that depend on the speed of the environment. So at the beginning, when the speed is not fast, the performance of the average Whittle index is not necessarily good. But when we take the speed going to infinite, we can see that here in the first line, we have the result for the optimal, the performance for the optimal policy, and we have the performance for the Whittle index policy. And we can see that when we take gamma to infinite, the performance of both policies are going to the same value. So the policy we propose is going to converge to the performance of the optimal policy as well. That is what we can show with our simulations. So this closes the idea that we can show that we have a set that is going to be asymptotically optimal for our problem. And then is when we wanted to change a bit the conditions and the hypothesis. How much time do we have?
20 minutes.
Sorry, great. Is there any question up to here? No? Okay, because I'm going to change now some hypotheses. I'm going to talk about our second problem. In our second problem, we are not going to scale the environment. We're not going to take the speed of the environment to infinite. So in this case, we change the framework directly. So we're working now more, they are still bandits, but they have more an interpretation as queues, because we're going to study a particular case. We're going to study a case with abandonments. This means we have queues with arrivals, and we have queues with service. And we also have abandonments, so people that waiting for service can abandon the system. This is interesting because this changes the dependence on the state, and this is like bandits that are restless, because even if we don't serve the queue, we may have people that abandon the system. We're going to consider an environment that has only two states, and the interesting point here is that we are going to consider observable policies. What does it mean? That are policies that are going to depend on the state N of the bandit and D of the environment. Okay? What does it mean? We're going, for example, if we have only two bandits and we want to choose which one to serve, we are going to check the state of the bandits. So if they are queues, we may compare how many customers have any queue, each of the queues. But we are also going to see in which environment we are now. Okay? We can see the environment, and we can take policies that see the environment to decide which queue to serve. This is new. This is not what we did in the first problem. And this makes much more complicated the problem, but also it gives us some other overview that we can use. We are going to work directly in the relax problem. We are going to use the Whittle's relaxation idea. So we are going to work in a one bandit problem to get some ideas to show for the relax framework. And in that case, we have this kind of, the performance depends on the, we have still this expected cost for each policy. So if we fix policy N1 and 2, when I say N1 and 2, it means we have a threshold policy. It means that the policy N1 and 2 makes that if we are in the first environment, we are only going to serve the bandit if we have more than N1 customers. If we are in second environment, we are going to serve the bandit only if we have more than N2 customers. And for that policy, we can get this formula for its performance, which still depends on the multiplier W, because we're in the relaxed problem. And we are going to compare the different performances for different threshold policies. So the first point we proved is that the threshold policies are going to be optimal. So the optimal policies, we can get them among the the threshold policies. That's interesting.
M is a vector here?
Yes, n is going to be this vector, n1 and 2. So we have,
M.
M. No, M are the different states of the bandit, different customers. So yes, maybe it's not that clear. Do I have somewhere to write? No. No, it's okay. What I mean is, no, it's okay, sorry. What we have here is, yes, maybe I put the formula, but it's not that clear at once. We have here a threshold policy, n1 and 2. It means that we are going to compare, we see the state of the bandit and the environment. So at the beginning, we say that we have environment 1 or environment 2. If we're in environment 1, we only see n1, and we see if the state m of the bandit, so how many customers has the bandit in that moment, is over or lower than n1, which is the threshold for that environment. That's what we do. We can show that this formula, so the sum over different states of the bandit and different states of the environment, of the coast and the stationary measure, is going to give us the performance of this policy. And taking this policy and this performance, it depends on the multiplier W, and we compare the performance of different threshold policies. That's the idea. This is going to be a linear function on W. As you can see, there are fixed parameters that depend only on the threshold n. So we are going to have different linear functions for each threshold policy n. And what we can see is that we have, like, depending on the x-axis, we have the multiplier W. We have the different performance for different threshold policies. And we can see that for each different W, we are going to have different threshold policy that is the one that minimizes in that multiplier. That's what we saw. And what we can show, in fact, is that from this kind of problem, from this kind of comparison we can do, we can take the indices that work as a Whittle index for this problem. What do we mean? The indices in this case are going to be the crossing points of these linear functions. That's what we can show, because they are where we change which one is the threshold policy that is the minimizing one in that point. And doing this, what we can do is to define we can define a Whittle index for each state of the bandit and each state of the environment. That's what we do. Where the index for each state is going to be, I think, I'm not sure this is clear. We are going to have a fixed environment D. So for example, if we see environment 1, we are going to define the Whittle index for different states of the bandit in environment 1 according to the crossing point we have when we change from one minimizing linear function to a minimizing linear function. The idea, what we can, is not maybe that important how we get this Whittle index, but the first result we can get, and it's a clear result we get from this problem, is that it's going to be an environment that has a full priority against the other one. What does it mean with full priority? It means that we can show that according to the multiplier, to the Lagrangian multiplier we have, we are going to have that we have an index that depends only on the parameters of the environment, of the transitions of the environment. We can show that it's optimal to make all active in one environment before doing all active in the second environment. That's what we can get, and it's an interesting result we have. We didn't expect this when we started the problem, but then we got some ideas that drew us here. And this is what we are proving, what we have already proved. We are now trying to generalize this for more environments, but it's something interesting we got. And moreover, what we could show is that we have an...
Sorry, don't get what changed. So when you say environment there, you got the state.
Yes.
So two environments. So what my understanding was that the arrival rate of individual cubes was somehow indexed by the index on the environment.
Yes.
So I'm not getting how can it be that there's a priority? So
it means, okay, it's a good question. What we are saying here is we have just one cube, because the important thing here is that we are working in a relaxed problem. Okay, so when we talk about the relaxed problem, we're only watching one bandit. Okay, we're not watching all bandits at a time. And when we watch one bandit, we have to say in each state if we're going to make it active or passive. And that, according to the mood.
Okay, so in that state, for that bandit, the average arrival rate is higher, then you activate it. And then
yes, that's the point. That's the point. When we can find this, if we look just one bandit, and we have when we say that there's a priority, it means that for one bandit, if it is in this environment, it's going to be active, Optima is going to be active, and in the other one, it's going to be passive. That's what we can show, just for one bandit. And then we have to come back to the original problem with the idea with the deal. So this is just coming back to the original bandit problem, okay? But what we say here is just that just for one bandit, we can say there is a priority environment, okay? So yes, this is the first result. The second result is that we can show, in fact, there is an interesting expression for the environment and how to choose the priority between both environments. So the environment that is going to have priority is the one with the highest, this highest coefficient, which depends on mu and theta. That is a classic result for an abandonment queue, but it's also adding R1 and R2, which means the transition rates from the environment from going from state 1 to state 2. That is what we could show. So this means R1 is going from state 1 to state 2, and R2 is going from state 2 to state 1. This is the coefficient we need to use to compare. And the index for the priority environment, here it says D0, but it means DP, sorry, the priority environment. It doesn't depend on on n. So it's constant for all different states. It's only important that we are in the priority environment. That's the idea. This is our second result. We are now finishing this paper now. So I would like to sum up what we have up to here. We have two different problems. We have a first problem where we have restless bandits, where in both we have restless bandits that depend on the environment. But the first one, we have a fast changing environment. It means that when we scale the amount of bandits, we scale the speed of the environment as well. So we have to consider an observable policies. And for this case, we can find a set that is an asymptotically optimal set of policies. And we can show that an example policy, which is the average Whittle index. And we can show that has a good performance if we compute its performance. In the second problem, we consider a normal speed for the environment, and we study directly the relaxed problem, so one bandit problem. We consider abandonments, and we also consider observable policies, which can depend on the state of the environment. The results we get is that we can show that there is a Whittle index, and we can show it is the Whittle index. And what we also show is what I have just told you, is that we can find also in a priority environment where the index does not depend on n, does not depend on the state of the bandit. So those are the two results we have to here, and that's all. Thank you. If you have questions.
In the first problem, you get a solution which
yes.
is optimal in the limit.
Yes.
But so it's a relaxed.
It's for the relaxed problem, yes.
So how do you?
Then what we can say is that we have to consider two different things. It is optimal for the relaxed problem, and it is also optimal for the original problem in an asymptotical regime. So it also works for the problem where we have the fixed constraint. It's not only for the relaxed one. Then if we want to study the original problem, but not in an asymptotic regime, so when n is fixed, we cannot get a direct solution because it's still NP hard, is what Whittle showed in his first results. But however, in fact, for example, for the simulations we did, so here, in this, when we did the simulations for queues, in this case, we kept the amount of bandits fixed. So in fact, here is even more interesting that we can show that the policies we propose have a good performance here, even if we're not taking n to infinite. So it's not the asymptotic regime, it's just taking the speed to infinite, but the amount of bandits is fixed. So this is something interesting, and in fact, we have some ideas coming out from here.
But how many bandits are active?
Here we have two bandits and only one can be active.
Okay.
So in this model, it's not the mean field limit. Then, in fact, there's one interesting discussion after this, is why are we getting a good performance even if we are not taking the limit n to infinite? And we discussed, and we have some more ideas there about what to do. We think here we are getting a good performance because they are restless bandits, but they are not abandonments. So the only restless detail we have is that we have arrivals. And that is not that useful for a restless model because it's almost not restless. And now we are working also in another problem we want to work on, is in this problem, but adding abandonments to show that if we don't take n to infinite, it's not going to be optimal, even though here it looks like it's being optimal. Okay?
And how does it compare to, for instance, shortest remaining processing time?
Good question. I think in this case, I should go back to how Whittle index relates to shortest remaining process time. It's somehow related because what we have here is that it depends, these policies depend still on how many customers we have in each bandit, the state of the bandits, we can see them as the state of the queue. And usually one would expect to have more priority in the bandit that has, or not necessarily, more or less customers. I'm not sure. I should think about that. But why do you relate it to this kind of policies?
Well, it's natural.
Yes.
Just
Yes, I should think.
just I mean, do you do something? Do you learn how because you average over the environment, right?
Yes, now we are taking the average of the environment. So,
You don't have to learn the environment.
no, here, yes, the environment is given, yes. No, now I'm a bit lost. But yes, at the end it's just a scheduling problem. No, we have to choose which one we're going to serve. Yes. Okay, it's something I can think.
Since you didn't show the Whittle index, at the very beginning you start and then you show the dual representation, W, which is the Lagrangian times the activation, and then you show that it's good to do this when
we have an environment, yes.
But then what is the physics? So somehow you can interpret this as state of the queue, which is number of customers, and then...
Yes, originally what we have here is that we may depend. There is an important thing to take into account that even if we have a queue that...
My question was
yes,
already,
sorry.
so I'm a newbie, don't know what is the Whittle index, so what is the shape of that? So you didn't spell it out in your presentation. So
No, yes, it's true.
it seems like certain the queue as long as it's shorter than a given threshold, which is this magic Whittle index.
Yes, yes, it's true. Yes, I should come back to here. No. Yes, so we can get some for some closed expression for the Whittle index if we work with a concrete system with parameters and everything. So when we did here the simulations, here this is a classical queue with arrivals and service times, and in that case we can compute the Whittle index, but now I couldn't give something else than the formula, or I don't think there is a clear intuition behind that. However, I can try to give some intuition here in how we get the Whittle index for the case. The Whittle index is as you were saying, is a threshold. We have W. W is maybe I didn't say this, but it's an interesting interpretation. W, which is the multiplier, is some subsidy for passivity. It means that here in this formula, in this one, this one, the last one, we have the multiplier, something that is multiplying the factor 0 or 1, which is active or passive. So then here, if W is high, it's going to be more interesting to make it passive. So here we don't want this term because W, we want to minimize this, and W is going to be high. The other way around, if we have W going to minus infinity, so something negative, it's going to be more interesting to make it active. So W, we can interpret it as a subsidy. If we have more subsidy for passivity, as much higher is W, much interesting for us is make it passive. So the interesting point is that if we have this threshold, so this is the indexability condition, and this, I don't have much more intuition, but it's something that we can find it. If we have something like a threshold, it means that if we're going to make it, we can find for each state, so each state we have in B here, for each state we can show that it changes with W. If we make W higher, we're going to find that in a given moment, this going from 1, from being active, it goes to 0 to passive. It depends totally in the rates for this bandit. So this bandit has rates that depends on the service times and the arrival time. So at the end, it's still something that has to do with the length queue and also how fast we serve and how fast we have arrivals. But the interesting idea of the Whittle index is this threshold idea. It's the idea that if we make higher W, we're going to have more bandits to make it active, or to make passive. And in that case, we're going to find for each state where it changes. This is the intuition. Then yes, we could go to the formula. I don't have it written here for the case where we did the simulations, but I don't think we can get a real intuition from that. Okay.
Thank you.
Thank you.